in your everyday life, it feels pretty smooth, doesn't it?
Yeah, continuous, like rolling a ball up a ramp.
Exactly. Or
Yeah.
driving your car. You can be going 10 miles an hour, 10 and a half, 10.7. It feels like you can pick any speed.
Or like throwing a ball. Seems like you can use any amount of force, right?
Right. Energy feels like that ramp. You can stop anywhere along the way. But the sources we're looking at today, they take us deep down into the quantum world. Atoms, particles.
And down there, it's a completely different picture. Turns out energy doesn't behave like that smooth ramp at all.
Not continuous?
Nope. It's more like a staircase. Energy only exists in specific fixed steps.
A staircase. So you can be on step 1 or step 2.
But absolutely nowhere in between. That's what we mean by quantized energy. It comes in discrete packets or quanta.
And this is where it gets really fascinating, I think. Our deep dive today, based on these sources, it's going to show how this weird idea, this quantization, it actually comes directly from something really fundamental about quantum mechanics.
That's the core idea. It stems from the wave-like nature of matter.
Wave-like nature.
Yeah. We'll look at how the math describing these waves, the wave function well, just the simple fact of a particle being stuck in one place that actually forces its energy to come in these steps.
Stuck in one place.
Yeah.
Like confined.
Exactly. And believe it or not, a guitar string is actually going to help us visualize this. It's a great analogy for why electrons in atoms, for instance, only have certain allowed energy levels.
Okay, so our everyday energy ramp versus the quantum staircase. Let's build that staircase. Where do we start?
Well, the foundation is something called wave-particle duality. It's maybe one of the strangest parts of quantum mechanics, but absolutely essential.
Right, the idea that things like electrons, which we normally picture as tiny dots.
They don't just act like particles. They also have wave properties. They act like waves sometimes.
That still kind of breaks my brain a little. A particle and a wave at the same time.
It is weird, but that duality is key. And we have a mathematical tool for the wave part, the wave function, usually written with the Greek letter psi-phi.
Psi-phi. And what does that wave function actually tell us about the particle?
Well, it's not like a wave on water where the height tells you something direct. The value of psi itself isn't directly physical, but its magnitude squared at a certain point in space tells you the probability of finding the particle right there if you were to look.
Ah, okay, so it's about probabilities. Where you're likely to find it, not exactly where it is.
Precisely. It carries the wave information like wavelength, which relates to the particle's momentum.
Okay, so psi describes the wave nature, but what controls how this psi wave behaves? What are the rules?
That's where the Schrödinger equation comes in. It's sort of the master equation for the wave function.
The famous Schrödinger equation.
Yep. For situations where the energy isn't changing over time, we often use the time-independent version. It looks like this. HKI equals EP psi.
Looks simple enough, but let's unpack those symbols. H hat.
H, yeah, the little hat means it's an operator. It basically represents the total energy of the system, kinetic plus potential energy, all wrapped up in a mathematical procedure.
Okay. So 8 is like the calculate total energy instruction.
Yeah.
And psi-i is the wave function we just talked about.
Right. And E is just a number representing the actual specific constant energy value for that particular state described by TEF.
So the equation says, apply the energy operator H to the wave function.
And if there's a valid state for that system, you just get the same wave function back, but multiplied by the energy value E.
That sounds special, like only certain waves work.
Exactly. It's a specific type of equation mathematicians call an eigenvalue equation. H is the operator, Airy is an eigenfunction, and the energy E is the corresponding eigenvalue. It tells us that only certain wave functions, certain MELs, are solutions, and each one has its own specific energy E.
Okay. Eigenvalue equation. But still, why does that mean only specific E values? Why not a whole smooth range of energies? Why the staircase?
Ah, that's the million-dollar question. The equation itself isn't the whole story. The missing piece is something called boundary conditions.
Boundary conditions. What do boundaries have to do with energy levels?
Everything, it turns out. Imagine a particle just floating freely in empty space. No forces, no walls.
Okay, completely free.
Its wave function can basically be any shape, any wavelength it wants. And if the wavelength can be anything, its momentum can be anything. Remember, de Broglie's P equals.
Right. Momentum depends on wavelength.
And if momentum can be anything, its kinetic energy can be anything. That's your smooth ramp. Continuous energy is allowed for a free particle.
Okay, makes sense. No restrictions, no energy steps.
But the moment you confine that particle, say, you trap it in a box, or it's an electron held near an atom's nucleus.
It's not free anymore.
Exactly. Its wave function is now also confined. It can't just spread out infinitely. It has to sort of live within the boundaries.
So the space it's in puts limits on the wave.
Precisely. And these physical limits impose mathematical limits on the possible shapes it can take. Those limits are the boundary conditions. The wave function has to fit inside its container properly.
How does a wave fit? Can we visualize that?
Yeah, this is where that guitar string analogy is perfect. Think about it. A guitar string is fixed at both ends, right?
Tied down.
So when you pluck it, it vibrates, but only in specific patterns. We call them standing waves.
Like the main note and then those higher harmonics where you see points on the string not moving?
Exactly. Those points not moving are called nodes. And crucially, the points where the string is fixed must be nodes. The string displacement has to be zero there.
Okay, the fixed ends force the wave to be zero at those points.
Yes. And that condition zero at the ends means only certain wavelengths can exist on the string. You need a wavelength where exactly one half wave fits, or two half waves, or three. A whole number of half wavelengths has to fit perfectly between the fixed ends.
Ah, I see. The physical fixing dictates the allowed wave shapes and wavelength.
You've got it. Confinement leads to specific allowed wave patterns. Now let's take that idea and apply it to a quantum particle. The simplest model is the particle in a box.
Okay, particle in a box. What does that look like?
Imagine a particle, like an electron, that can only move back and forth along a line segment of certain length. Let's call it L.
Just one dimension.
Yep. And at the ends of this line segment, at exo and ectocell, there are infinitely high walls. Impenetrable.
So it's trapped inside this length L. It absolutely cannot get out.
Correct. Infinite potential energy at the walls means the probability of finding the particle at the walls, or outside, must be zero.
Probability zero. So the wave function, C chi, must be zero at the walls.
Exactly. That's the boundary condition for the particle in a box. So zero in stio and spio L in spero zero.
Hey, that sounds just like the guitar string. Zero amplitude at the fixed ends.
It's the very same mathematical condition. And just like the guitar string, this forces the wave function inside the box to be a standing wave. It has to start at zero, wiggle somehow, and end up back at zero exactly at the other wall, L.
Which means the length L has to accommodate a whole number of half wavelengths.
Perfect. The allowed wavelengths, L, must satisfy L equals n to 2, where n has to be a positive whole number, 1, 2, 3, and so on.
And n is?
That's our quantum number for this system.
Yep.
N1 is the lowest energy state, like the fundamental note on the string. N in 2 is the next state up, and so on. Each n corresponds to a different allowed standing wave pattern.
Okay. So confinement gives us boundary conditions, which means only specific standing waves fit, which means only specific wavelengths are allowed, determined by L and this number n. But how does that lock down the energy?
Great question. We connect wavelength to energy in 2 steps using fundamental physics principles. First, the de Broglie relation momentum P is Planck's constant h divided by wavelength O, P equals it.
Okay, so if only certain loos are allowed?
Then only certain momentums P are allowed. The momentum is quantized too, indirectly.
Got it. And energy.
Well, inside the box, we said the potential energy is zero. So the total energy E is just the kinetic energy. And kinetic energy is related to momentum by E equals pi p equal 2 meters, where m is the mass of the particle.
Ah, I see the chain. Boundary conditions give allowed all. Allowed all gives allowed P via de Broglie. Allowed half T gives allowed E via the kinetic energy formula.
Exactly. Let's follow it through. We found the allowed wavelengths are E equals 4ln. Substitute that into de Broglie. P equals h2ln equals hln2l. These are the allowed momentums.
Okay, momentum depends on n.
Now substitute this allowed momentum P into the energy formula E at Olsen T P Q L. N equals h n ln s. Let's square the top term. That's HOS 4ln 4ln and then divide by 2 meters. We get n ns n ln s 8 n ln.
Wow. Okay, E sub n. The allowed energy depends on n squared.
That's the punchline. Since n can only be 1, 2, 3 page, and n isn't allowed, it would mean psi is 0 everywhere, no particle. The energy E can only take on the specific values corresponding to n1, n2, n02, etc.
E 0, discrete values.
That's your staircase. The energy is quantized. Notice the Angela-Tennant dependence, the steps get further apart as you go higher in energy. EO is 4 times EO. EO is 9 times EO. But they are distinct, discrete levels. No energy between EO and zeros is possible for the particle in that box.
That's actually elegant. It's not just some rule someone made up. Quantization falls right out of the wave nature plus confinement.
That's the beautiful realization. Boundary conditions restrict the wave functions to standing waves. Standing waves have specific wavelengths, momentums, and those translate directly into specific discrete energy levels. The wave nature, when constrained, builds the staircase.
And this isn't just for a toy model like the box, right? This applies to real things.
Absolutely. Think about an electron in an atom. It's confined, trapped by the electrical pole of the nucleus.
Okay, the nucleus provides the confinement.
Right. Now, solving the Schrödinger equation for the electron's wave function in the atom's potential field is way more complicated than the simple box. It involves 3 dimensions, but the principle is identical.
Boundary conditions still apply.
Yes. The condition is basically that the wave function has to fade away properly far from the nucleus. Solving the equation with these conditions, again, yields only specific discrete energy levels that the electron is allowed to occupy.
And that's why atoms are stable.
Yeah.
And why they give off specific colors of light.
Exactly. Those discrete energy levels explain atomic stability. Electrons can't just spiral into the nucleus, losing energy continuously. They can only sit on the allowed steps. And the specific colors, the spectral lines we see when we analyze light from atoms, those correspond to electrons jumping between these specific energy steps, emitting or absorbing photons with energies exactly equal to the difference between the steps.
So the staircase is real. It's built into the structure of atoms because electrons are confined waves.
That's the picture quantum mechanics gives us, a fundamental shift from classical thinking.
So what does this mean for you listening to this? Well, this whole idea, quantized energy derived from wave nature and confinement, it's not just abstract physics. It's why matter is stable.
It underpins chemistry, why certain reactions happen and others don't.
Yeah, and it's crucial for so much technology we rely on. Lasers, semiconductors in your phone or computer, MRI machines, they all work because energy comes in these discrete steps at the quantum level.
It's really seeing the fundamental graininess, the stepped structure of reality itself.
So we started off contrasting that smooth, everyday energy ramp with the surprising quantum staircase.
And we saw that staircase isn't just put there by decree. It emerges naturally from the fact that matter behaves like waves.
And when those waves are confined, like an electron in an atom or particle in a box,
Or even like a guitar string fixed at its ends.
the confinement forces the waves into specific patterns, standing waves.
And because a wave's pattern is linked to its energy, only specific discrete energy levels become possible.
It's a direct consequence, really. This idea explains so much, from why atoms don't collapse to the specific frequencies of light emitted by stars.
Yeah, it's a powerful example of how the sometimes strange mathematical rules of quantum mechanics lead to very real observable features of the universe.
Okay, so here's something to chew on as we wrap up. We saw how confinement, being trapped in a box or near a nucleus, creates these energy steps. If simple confinement is the key ingredient, what other situations, maybe less obvious ones, out there in the universe might also be governed by similar hidden quantum staircases because of some form of restriction or boundary?